In 1917, German mathematician and physicist Albert Einstein published his paper entitled Cosmological Considerations for the General Theory of Relativity. In this paper, Einstein makes an addition to his famous field equations by adding the constant denoted by lambda, which he calls the cosmological constant. The reason that he adds this to his equations is so that the universe does not collapse under the force of its own gravity. Einstein had no idea, but he had just given us a promising candidate for the answer of one of the most complex questions in modern physics. That question being, of course, what is dark energy? The evidence supporting that dark energy exists in the first place is that 1. The universe is expanding, 2. The rate of expansion of the universe is increasing, and 3. The universe is very, very flat. Because of this flatness, there has to be a very specific average density of matter within the universe. We looked through our telescopes, we made some measurements, not even close. All of the matter in the universe, dark matter included, could not even make it halfway, only accounting for 30% of the necessary mass. This means that dark energy is basically everywhere. So we know it exists, but what is it? The short answer is, no one has any clue! The leading theory is that Einstein's cosmological constant represents dark energy in the universe. And while it does have the most supporting evidence, it does come with its own host of issues. Several quantum field theories would require the cosmological constant to have a value over 10 to the 100 times larger than it's been observed to be. However, we can kind of put this off as just saying that those particular theories need to be revised because the effects of vacuum energy predicted by the cosmological constant have been observed in a laboratory. If you're going to listen to Occam's razor, I'd say choose the cosmological constant. However, there are alternative theories. An explanation is a weak scalar field called quintessence being the real explanation for dark energy. The difference between this theory and the cosmological constant theory is that the quintessence field would have different values depending upon time and space. No evidence has been found of this particular idea, though. Another idea states that measurement artifacts, incorrect data, or space expanding more rapidly in the voids around our local cluster could give the illusion of space expanding universally faster than it really is, meaning dark energy just doesn't exist. Now it's time for the conclusion. The main question here is what is dark energy? And the answer? Nobody knows. But another question that's pretty important about dark energy is what will it do to the universe? In a few trillion years, the universe will be very, very lonely. And on that bright and happy note, it's time for me to go.
It's you. How are you, gentlemen? All your messes are belong to us.